So Jan Shawe-Taylor is the head of the department in computer science department of UCL, and he has been working for more than 3 decades, I think, or 2 decades, I don't know, in the field of machine learning, when machine learning was something that was not so popular. To say something about him, he's the only person I know who has a trophy for having over 10,000 citations of a book, which I think is quite an achievement for disseminating knowledge about machine learning to the world. And this is part of the topic he's going to talk today. And I don't think he needs much more presentation, and I let you with the talk.
Thanks, David, and thanks, Amparo, for the invitation. And it's great to be here in A Coruña. So, when I was thinking about what to, and asking David what to present, you know, the main idea was to talk about this work we've been doing together with David and Alex Bird on scaling nonlinear SVMs to very large data sets. But David suggested it would be good to give a little bit of background on kernel methods and perhaps some more recent other applications of these approaches. So I'm going to introduce that sort of approach to machine learning and also perhaps do it in a slightly different way than is more traditionally done. So I'm going to experiment with you in that sense. I hope you don't mind. So the background is that kernel methods have been a very successful approach to machine learning that has created a compromise between flexibility and principled regularization. So more recently, there's been a resurgence of deep learning, and sort of put in context, what I would say is if you've got tons of data, you know, deep learning may be able to do a better job. If you've got less data, the sort of way in which kernel methods handle the regularization may actually be preferable. So there's a sort of trade-off here between the amount of data you have, the flexibility of the model that you want to use, and the fit of the model to the particular type of data. And deep learning is proving to be particularly good at handling images and also speech and so on. So there's something about that data that is particularly matched with the structures of the deep learning architectures. I think it's still perhaps not as well understood as it might be why that is the case and what's happening there. And I'm certainly not going to talk about that today, but I just wanted to sort of put that in context. If you're in that situation with lots of data and you know that a deep learning architecture is the right architecture for that data, great. If you're perhaps in a situation where you're less certain and with less data, kernel methods are perhaps a good choice. So that's a sort of background context on that. I think the other thing to say about kernel methods, they've been extended in many ways to make them usable in different applications. And for an example, I'm going to talk about an application in reinforcement learning to give you a flavor of some of the things that have been done. So in terms of the problem of scaling to very large data, SVMs exhibit what's known as dual sparsity. I'll get into a bit more detail on what that is later on. Basically, it's the solution is expressed in terms of some subset of the training data. So you have your training data, you run your algorithm, and then some subset of that data is used to define the solution, the learned classifier or regressor or whatever it might be. So that's fine. The problem is that it proves to be a bottleneck with very, very large data sets. So typically it might be a very small proportion of the training data that actually is used in defining the solution. But still, when you're up into the millions and millions of data points, that proves to be impractical, and both for the training algorithm and for, of course, evaluation at test time, when you need to effectively compare your test point against all of those chosen training points that you have, the so-called support vectors. So the support vectors are those that are used to define the solution. So this has proved a bottleneck in very large data applications. So this is perhaps the core of what my talk will be about towards the end. One norm regularization, on the other hand, controls primal sparsity. So that is really the number of features. If you have an explicit set of features and you want to restrict the number of those features that are involved in defining your solution, then you can use what's known as a one norm regularization. And that, again, we'll talk about that in the talk. And I'll mention the link to multiple kernel learning. So what I want to do, give an introduction to kernel methods, discuss, now this is the new take that I wanted to sort of give to you, is this distribution embedding methods. So how do you embed a distribution into a kernel-defined feature space, and then the application of that approach to reinforcement learning. So that will be my introduction to kernel methods. I'm then going to talk a little bit about the sort of contrast between the two-norm regularization of SVMs and the one-norm that I mentioned just a moment ago, which is referred to as linear programming boosting, or sometimes one-norm SVMs, or sometimes, I mean, it has a number of names, but I'll be using linear programming boosting. I'll then show the connection to multiple kernel learning, and hence demonstrate this method of scaling nonlinear SVMs to sort of map-reduce scale big data applications. So that's the outline. Okay, so here's my tutorial on kernel methods. So kernel methods basically are using an implicit representation of a feature space. So in order to learn, you need to represent your data in some way. And the way that's used in kernel methods is an implicit representation. You don't explicitly compute your features, but you represent them through what's known as a kernel, which is this function kappa here. And what that represents is the computation of an inner product between the actual feature vector, which I'm denoting by phi of x. So x is my input, phi of x is my features that I compute from my input, but I'm again not actually going to compute them, but they're implicitly defined by this phi of x, and here's another input z, and I'm computing the features phi of z of that, but rather than actually computing these, I'm going to make do with this function that computes an inner product between those two sets of features. And so I now have to convert all my algorithms to work with this inner product function rather than with this explicit feature representation. And that's essentially what kernel methods are doing in a nutshell. They're using this as a proxy for the features, and this enables you to work in very, very large feature spaces, potentially without having the cost of actually explicitly. I mean, this feature vector can even be infinite dimensional, and you can still do computation. So that's the trick. So the properties of this kernel function that you require in order for it to define a feature space. So we think now, rather than thinking about defining feature spaces, we think about defining kernel functions, and through them implicitly defining our feature space. So what are the properties that make a kernel function kosher, that it really does define a feature space? Well, one of the properties is that it should be symmetric. If we swap the order of the two arguments, x and z, the inner product should not change, so it has to be a symmetric function of its two arguments. And the other property is that the kernel matrices that you define on a set of training points, so if you think of now taking a set of training points, x1 up to xm, let's say, and we create a matrix whose entries are the inner products or the kernel computation between the ith and jth training point. So it's a square matrix. You know, rows are the training points and the same training points in the columns, and the ij entry is the inner product, or in this case, computed by the evaluation of the kernel function between those two. If we look at the outer product of this kernel matrix with an arbitrary vector u, we can write this in this way and then bring the sum inside the inner product. So the sum over the ui goes with this one and the sum over the uj with this one. And this actually turns out to be the norm squared of this vector in the feature space. So that tells us, since this is a norm squared, if it was a proper kernel function defined a feature space mapping, then this must be a positive quantity, a non-negative quantity. So what it's saying is that this is effectively saying that this matrix is positive semi-definite. This is another way of saying that it has no negative eigenvalues. And this is for any arbitrary set of training points. So any training points, any set of data points in the input space, you create a kernel matrix, it must not have negative eigenvalues. Now, it turns out that those are the only two properties you need. Symmetry and that slightly confusing property of non-negative eigenvalues. So basically, if you have a function that satisfies that it's symmetric and every kernel matrix is positive semi-definite, then it defines a feature space. And you can use it for any kernel methods algorithm. So it means, in addition, that we can define kernels on virtually any type of objects, on documents, graphs, networks. So all we need to do is to have a way of computing this function that I described on the previous slide. This can be basically, so don't think about this part anymore, just think about this function. We just need to create that function that satisfies these two properties, and the objects x and z can be any objects that we're particularly interested in calculating or learning over. So they could be networks, they could be documents, graphs, whatever or more complex objects involving subcomponents, whatever. All you need to do is define this inner product function in such a way that it's positive, semi-definite, and symmetric. Once you've done that, and as I say, it's a sort of generic way of operating, then many standard linear algorithms that traditional statistics is used, or can be transformed into a dual representation of the weight vector, and therefore can be used in this kernel-defined feature space. The critical thing you basically need is this two-norm regularization. And the reason for that is, intuitively, if you're in your feature space, you must find your solution in a linear combination of the training data. So any orthogonal component to that space spanned by the input data must have zero weight and the way to ensure that happens is to do two-norm regularization. So that's basically kernel methods in a nutshell. And you can do things like regression with so-called ridge regression, kernel ridge regression. The ridge is basically the two-norm regularization. It's a normal linear regression with a two-norm regularization, and you can apply it in a kernel-defined feature space. Principal components analysis, canonical correlation analysis, support vector machines, which I'll talk about a little bit more in a minute, and so on. Okay, so that's the sort of background. Now, what I'm going to do now is just give you a little bit of an outline of the proof of that fact that the kernel function defines a feature space. And the reason I'm going to do that is it's going to give me this sort of lead into the kernel distribution embedding stuff that I'm going to talk about relative to reinforcement learning. So this is sort of leading now to the sort of example of applying kernel methods in reinforcement learning. So the way you actually do it is you create a feature space, F. So F is going to be my feature space. Now the points in that feature space are actually functions. So it's a little bit weird. You map your input points to functions. So the points are now functions, and they're defined in this way. They're a finite combination of a weighted combination of a kernel evaluation at an input point. So at some point in the input space, let's call it x1 up to xm, are chosen, and I choose some weights, alpha I, that are real numbers, and I create the function that effectively evaluates the kernel at that point and the argument of the function. This is the argument of the function, so this is a mapping from some input point into a real value. So it's a real valued function on the input space, and those are the points in my feature space. Slightly weird, okay? But that's what you do, and you make it an inner product space by defining the inner product in this way. The inner product between the function defined on a point x, so the mapping from input space to the kernel evaluation at a fixed x here, and the function defined by z, the inner product between these two functions is actually kappa of x comma z. And the way we embed the input space into this space F is we map the input x into the function that evaluates a point relative to x. So these are, just to repeat, these are functions. This is the way we define, I mean, this defines the inner product only on these simple functions. For these composite ones, clearly this will define how we do an inner product between two such functions by just using the fact that the inner product, it can be, you can take the sum inside the inner product or outside the inner product. So we are able to evaluate inner products between general points here. And the interesting property is something known as the reproducing property of functions in this space F, points in this space. If we want to evaluate a function in this space, f of x is actually just the inner product between that function and the embedded image of the point x. So to evaluate f at x, we actually just take f inner product. And if you think about f being defined in this way and the fact that the inner product does this, this will actually just evaluate the function at the point x. So this is known as the reproducing kernel Hilbert space. Okay. So hope that's not too confusing, but it's really just to give you the framework within which I can then define this embedding of a distribution. So if you have a distribution on the input space now, then you can define the embedding or a point, if you like, in the feature space that represents that distribution. And it's just the expected value of the image of an input point expected over the distribution. So the distribution is on the input space. We look at that expected embedding, and that is a point in the feature space which it represents that distribution. And we can also do an empirical counterpart. If we have a sample from a distribution, a finite sample, we can take the finite sum, or the finite average, sorry, of those images in the, and that's an empirical estimate of this point, mu p. So mu p is a point, unique point defined by the distribution. Mu hat s is an empirical estimate of that point. And there's a sort of, I think, a nice result that sort of captures the power in a way, or the fundamental idea behind kernel methods, which is that with high probability, those two points are quite close in, not in the feature space. So in other words, mu hat, this empirical, is a good estimate of mu p, provided the distribution has support in a radius, a ball of radius r, sort of fixed. So the support of the distribution in the feature space is bounded. So I won't, I mean, for those of you who are familiar, if you have, for instance, a Gaussian kernel, which is one of the kernels that is frequently used, then r is 1. The image of any point has norm 1 in the feature space. So in that case, a Gaussian kernel R would be 1 here. So this is a sort of 1 over root m convergence m is the number of the size of this set of points here, this sample. So we've got a 1 over root m convergence of this empirical estimate to the true embedding point of that distribution with probability 1 minus delta over this random sample. Now this is sort of surprising given that we could be in an infinite dimensional space. So we're sort of somehow avoiding the curse of dimensionality. So we're working in this very potentially high dimensional space, and yet we're getting some sort of good estimates with relatively small, good convergence estimates. So this is sort of capturing, I think, the essence of what's going on with the kernel methods. And just as an example of applying how you might use this information, if we were interested in evaluating expectations of functions, so remember that F is a space of functions, let's take an F in that space of functions. These are the feature vectors. The expectation of the function x, use the reproducing kernel Hilbert space property that f of x is just the inner product between f and phi of x, the embedding of x. Expectation of x we can take inside the inner product. This is just our mu p, and so to compute expectations we can actually just take an inner product with this single point. And furthermore, we can do the same with our empirical estimate, and we can bound the inaccuracy of doing an empirical estimate of this expectation of f in terms of because we can take again this linear inner product and bound this by Cauchy-Schwarz. We know the bound between mu p and mu s. We just did that on the previous slide. Here's the norm of f, and this is the previous expression. So we're able to get good estimates, even though we're doing this in an infinite dimensional feature space, of the expected value of a function. So that's sort of, I think a nice property, and actually proves the key property in terms of applying this to reinforcement learning. So in reinforcement learning, a lot of what you're if you're learning a model of the behavior of the dynamics of a system, so just a quick sort of, I'm not going to give you definitions because they, turn into many slides of reinforcement learning, but basically what you're trying to do in reinforcement learning is to train an agent to act in some environment. So there's an action space, and they can take actions. They might be a robot walking around. They receive reward, and at the same time they're trying to learn about the space. In other words, the states that they can reach, how their actions actually affect the state of the world, and how that affects the reward that they receive. So there's a sort of whole process of learning how to get reward, but also what the effect of your actions are. So you're building a model of the world and how to operate in that world. So it's very natural then to ask about conditional distributions, because what you're interested in is what is going to be the expected consequences of taking certain actions. So here, the y in our reinforcement learning application is going to be the actions that you might take, and the x is the expected state of the world that you might reach when you take that action. So now you actually are interested in mapping not just a single distribution, but a conditional distribution. In other words, a distribution for each value of y. So a sort of a mapping from y, your action space, into your feature space. And you can just view that, because this is just basically a Euclidean or a Hilbert space. You can view this as a regressor. So learning to act in the world comes learning a regressor in this way of viewing things. So I'm not going to go into the detail of this, but this is basically the algorithm that follows from that, of learning and some sparsification using matching pursuit. But essentially you're learning from experience what the effects of your actions are, and then learning to optimize the reward. This R here is the reward, and then policy improvement that you can follow to improve the reward that you get. So here's some examples of applying that. This is a very kind of classical problem of balancing a pole. You've got a cart and you can apply a force, and you're trying to apply the force, so the action you take is just apply this force in order to keep this pole balanced above the cart. And the states is just a two-dimensional state, so it's quite a simple case of theta and which is this angle, and the rate of change of theta. And these are the different methods. The sort of more standard method is this KBRL, but using this conditional mean embedding is the green one, and then with the sparsification method to keep the thing manageable is this compressed conditional mean embedding, and this is the cumulative discounted reward that's achieved after what are really very few training iterations. So literally within 10 iterations of trying this thing, you're already able to balance the pole pretty effectively. So it's again a kind of able to use and infer from that learned understanding of the dynamics. So it's learning the dynamics here. You're not programming in any of the physics. You're actually getting it to learn the physics of this environment. It's able to learn the physics and how to optimize its reward. So another slightly more complicated example is a quadricopter simulator where you've got a state space with 13 dimensions and a three-dimensional state action space of possible velocity vectors that you can choose, and you're trying to navigate to a certain point or have a holding pattern. The one I'm going to show is this navigation. So again, you're able to learn the sort of effect of your actions on the states and how to optimize the reward that you get very much in relatively small number of training iterations using this approach of the reproducing kernel Hilbert space controller. And this is a little dig at deep learning, that it actually proves quite difficult to do this for deep learning for various reasons, but the sort of data sparsity, this is learning with relatively small amounts of data. Okay, so that's my little introduction to sort of a new take on applying kernel methods in reinforcement learning and some of the background. What I'm now going to cut to is support vector machines and looking towards how to scale them to very large data sets. Okay, so that's the sort of into the second part of the talk now. So let's just step back. Remember, we've got this kernel-defined feature space, and we're trying to learn now a classifier. So support vector machines are classifiers. And what we're thinking, the first thing to say is support vector machines are incredibly simple. All they are is a linear function in that kernel-defined feature space. Remember, phi is this mapping into the feature space. You can forget about all those function stuff now. Just think of it as a feature space. It's just some feature space, however it's defined. So this is a linear function in that feature space, plus maybe an offset. And we're going to try and learn that weight vector, W, in that feature space, implicitly through this dual representation. So we're going to learn it as a linear combination of the training data. And I'll show you what the linear coefficients are, but this is the optimization that we are actually trying to solve, expressed in the primal. So we're trying to solve a linear function that gets a classification correct. So this is the label times the linear function that we're using, this g, and we're trying to get it bigger than some gamma, which is a positive quantity, a margin. Perhaps some of the data points will fail to meet the margin. That's these so-called slack variables psi I, which must be positive, and we minimize or maximize the margin with minimizing the size of these slack variables. So that's the task that we're asking the support vectors to solve, and we're constraining the 2 norm, this is where the regularization kicks in, to be at most 1. So this is the support vector task. It's trying to separate the data with as large a margin as possible while constraining the weights to have norm 1 in this feature space. So again, keeping that control, and we're trying to maximize that margin gamma while keeping some of these slack variables small. So it's basically separation, linear separation in the feature space. Now the nice property is that if you take this optimization, firstly, it's actually a convex optimization, so there's a unique optimal solution to it. And so you don't have worries about local minima or any of that sort of stuff. But if you actually move to the dual of this optimization, so because it's convex, you have a convex dual as well, this is the form that you actually have. So it's this is the thing you minimize over alpha, so these are the dual variables. They turn out to be the coefficients that represent that weight vector in terms of the training data, the alpha i's. They are positive, and the representation of the weight vector W star is, I haven't written it out, but it's a alpha I star yi phi of xi. So it's a linear combination of the training data where the coefficients are alpha I, yi. And this is the thing you minimize, which is basically the norm of the weight vector, effectively. And, I mean, slightly rescaled, but, and the constraints that you have are 0 less than or equal to alpha I less than c, less than or equal to c, where c was this parameter controlling the relative strengths of the margin and the slack variables. The sum of the alpha i's is 1, and this is the constraint, another constraint. So very sort of clean dual representation. Again, it's convex, of course. You can plug in any standard solver. I mean, I'll give examples of using libSVM later. So not a, it's a very straightforward thing to use nowadays. And the very nice property is that many of these alpha I stars turn out to be 0. This was the property I referred to, that only a small subset of the training data is actually used to define the weight vector that you use in the application. The problem that I mentioned is that in very large data applications, that number is still too big. But still, for modest sizes of training data, that is fine. Alpha I star, a small subset is non-zero, and you use that to evaluate your test point. So this is the test evaluation, is now just a sum over the so-called support vectors of this weight times the label times this kernel evaluation of the test point with the corresponding training point plus this offset. Okay, so that's the SVM. I'm now going to talk about what I call linear programming boosting. So if I just go back to the SVM, what I mentioned here is this 2-norm regularization, which allows us to work in this kernel-defined feature space. If we move to the linear programming machines, we're going to make it a 1-norm regularization, but that means we have to have explicit features rather than that implicit representation. So HI I'm now using to represent a primal feature representation. Think of them as weak learners, if you like, as another possibility. But this is a potentially very high dimensional set of features. For each training point, J runs over a large number, I'm going to say capital N set of features. And we're going to have basically the same optimization as we have for SVM, apart from those two changes, explicit and a 1-norm representation. Same margin, and I've changed C to D, but it's just a constant, and some of the slack variables. And now the dual has this form. So we minimize a beta. Again, it's a convex optimization. It's actually a linear program now. The other one was a quadratic program. This is just a linear program. And these are the constraints. The UIs, the dual variables sum to 1, are positive. constrained by capital D, and this constraint applies for all the features. So for all the features, sum ui, yi, hi, j, this is for all j, is less than or equal to beta. And the final test evaluation is just a sum over the selected features now of wj star hj for a test point h here. So this now is a small sum because of the primal sparsity, okay? So the dual sparsity was SVM, this is the primal sparsity. So we seem to be caught between, either we use a kernel method or we have, we have dual sparsity or we have a sort of primal sparsity using this linear programming boosting approach. Okay, so now I'm going to talk about a sort of connection between these two, which is multiple kernel learning. Before I do that, just this is the algorithm that comes out of that linear programming approach. So solving essentially this or this approach, you have what I'm calling the linear programming boosting algorithm. Essentially, you have an iterative method where you start with, you work with some distribution over the examples, and you generate features that you need to use in order to improve the solution. So you start with a small set of features, and then you add features iteratively. So remember, the features perhaps a very large set. You're starting with a small set, and you're just adding them as you need them in order to arrive at the optimal solution. And the criterion for adding a feature is this fj, which is this quantity here. You evaluate. This has to be less than or equal to beta for all of the features. So basically you solve with a subset of features, get a beta. If this quantity is bigger than beta, then you know that feature has to be added in, and you add it in and iterate in that way. And that's essentially what's happening here. We add in we look for the maximum of this quantity. If it's bigger, if it's less than beta, then we're done, we exit. If it's not, then we add it, and we solve again and iterate around. So there's a few things to note. UI is a distribution on the examples. That comes from the property here that sum UI equals 1 and it's positive. Each j added corresponds to a sort of extra feature or weak learner. Fj is simply a weighted classification accuracy, this quantity that we're using to evaluate. And so we've effectively got a sort of boosting iterative algorithm, and we're guaranteed to converge, and there's a soft stopping criterion. So that's sort of the context for the linear programming approach. So the multiple kernel learning sort of ties the two together. Multiple kernel learning is essentially learning with a kernel that is taken to be a linear combination of a set of kernels. And now think of this n as our feature space, but now our features are kernels rather than individual features. But we have this same one norm regularization of now the combination weights. So the weights with which we combine the kernels are positive weights and sum to 1. So this is where the one norm comes in terms of the different kernels. Despite the fact that we're learning an SVM with this sort of ill-defined kernel, we're optimizing these Zs at the same time as we're learning the SVM, it remains a convex problem. And it would appear to be in significant danger of overfitting. So there's a question of how this performance scales with n. Now, I've got a few slides on that. I think I'm going to skip over those, but we can, just to summarize what I'm going to skip over, the argument can be made that this actually dependence on n in terms of the off-training, test performance is actually very benign. There's basically a logarithmic dependence on this number of kernels n in terms of if we do the generalization analysis. So I'm going to just quickly motivate that. I mean, the Rademacher complexity is the analysis tool that we can use to analyze that generalization. And if I'm going to skip through, but basically we get a probability of our classification error on a test point bounded in terms of these slack variables and this Rademacher complexity of the union of these spaces, which is the space of functions we can represent with individual kernels with bounded weights. This is a 2-norm bounded by 1. And so if we can bound the Rademacher complexity of this union, a very large union over these feature spaces, functions that we can represent with the individual kernels, then we're in good shape. And the bound that we can get depends logarithmically on the number of those kernels. So what this is telling us effectively is that there's a sort of a logarithmic dependence on the number of kernels in terms of the generalization bound. So that's just a reference there. So this is experimental results not done by us, but that sort of confirm this theoretical observation, which show that actually using very large numbers of kernels, using in a visual object challenge, so this is computer vision classification, they were able to get a significant improvement in a large number of these categories of classification. This was the Pascal Visual Objects Challenge back in 2007. This was the Daldy, Gulsham, Lama, and Zisserman. So I think, it was effectively, if you like, a practical demonstration of the power of multiple kernel learning when you throw lots of kernels in. So the kind of take-home message was, the one-norm regularization can control the cost of having very large numbers of kernels. So now the question, I'm bringing the two together now. So we've got the multiple kernel learning support vector machine, and I'm sort of suggesting we can use the linear programming boosting approach to training multiple kernel learning, and that is through this observation that if we want to maximize, this is the thing that chooses the weak learner, right? We look for the maximum of this over all choices of kernels, where this was the UI, sum ui yi w phi t of xi. So this is the property that we were trying to maximize in order to choose the kernel. But if we're doing this in a linear space, you can actually compute the solution exactly, because to sort of maximize an inner product, we choose w parallel to this vector here, which we've created by bringing the sum again inside the inner product. So this actually, we know how to solve exactly in that space, and this is the value of the solution. And the point here is that the UI is defined by the linear program, if you remember, actually now defines the weight that we're going to choose, and this is the weight that we have to choose in that space. So it's sort of telling us how to choose the weight in that feature space, and it actually has a dual representation in terms of those UI. So the UI defines the dual representation. So remember, the UI was coming out of the linear programming boosting algorithm. It's a linear program, now defines the weights of the dual weights in terms of picking a function from that kernel-defined feature space. So we can actually use the linear programming boosting to implement multiple kernel learning. Now the key idea here in terms of getting the scaling of support vector machines is to just apply that approach but with a single kernel. So the fact that we had multiple kernels here is not important. We can just think of it as a single kernel, and we have this method of selecting the next weak learner in terms of this dual representation. So each iteration adds a new column, a weak learner, to the master linear program. And the important point is that we know how sparse it is because it's defined by these UIs. So the sparsity of the UIs defines the sparsity, and that can be controlled by the number of columns in the linear program. So the number of weak learners we have already added controls the sparsity of the next weak learner that we add. So we're able to control how many support vectors we're actually using as we generate our solution, and we know that it will converge eventually to the support vector solution. So we can now distribute over a number of machines. We can compute a new column easily. We can solve the linear program because it's primarily sparse. We can iterate using a MapReduce style computation, and we have a measure of progress towards the global solution via the duality gap. So this gives us a sort of controlled way of gradually getting, if you like, a trade-off between the sparsity, the number of support vectors we're actually using, and the quality of solution that we're actually achieving with that level of sparsity. So that's the sort of the key way of controlling the sparsity. And here are some results on some modest-sized data sets, but the idea is to give you, this is just some preliminary results. So these are the 4 data sets. These are the size of the training data, number of features, and the size of the test set. And I'm comparing this, what I'm calling a linear programming SVM, with the libSVM. And these are the training times, and this is the accuracy. So this is basically after 100 iterations. So we're just using 100 iterations of the linear programming boosting approach. And you can see the accuracy is not quite there at the full accuracy, but the training time is roughly a half. In this case, this actually did less well. The training time was more, and the accuracy was still less. But in this case, the time was significantly reduced, and the accuracy was within, a whisker of the accuracy of the SVM. And on this one, this was the largest one, 125,000 data points. I mean, these aren't very large, I know, but this was just to give you an idea of how it scales. And in this case, again, a pretty significant reduction in time with a very slight reduction in accuracy. But this is just to take one of those, this web spam data, and show how the progress through iterations occurs. So as I said, these are examples with 100 iterations. So this 579 corresponds to this 579 here, and this is the accuracy, 98.62. This is the number of support vectors, so you can see how they're increasing compared to the number of support vectors of the libSVM. So this is a very much more manageable number. But even, with 50 iterations, the accuracy is only slightly less, and a significantly reduced number of support vectors. So we're controlling, if you like, the growth of the support vectors while the test accuracy is improving. But even with a modest number, we're already getting a relatively good accuracy. So clearly scaling on very large data, we would hope that, a modest number of iterations would get us a good accuracy while keeping the number of support vectors manageable across the many machines. So those are the results. So to summarize, I wanted to give you a sort of overview of kernel methods as a flexible tool that incorporate regularization in a principled way. I described the conditional mean embeddings approach to model-based reinforcement learning, highlighted the difficulty of scaling nonlinear SVMs to big data in distributed applications, and then introduced this method of approximating the solution by controlling the sparsity in a way that will be scalable to MapReduce implementations, and giving you some, well, pretty modest but initial encouraging empirical results. So that's the talk. Thank you.
Right, it's time for questions. If anyone has a question. In the very bottom, it's okay. It's working. Is it working?
No.
Is it working? Okay.
Okay.
My question is the following. In the first part of your talk, you mentioned the bound that resembles the square root of n consistency for your estimator.
Yeah.
And you mentioned that the only condition you need is that you have bounded with probability 1. In fact, the radius of your ball appears in the bound.
Yeah.
But my question is, don't you need that your feature space is finite dimensional?
No, that's the surprising thing about the result, exactly that. This is this result here. Sorry, where are we? Yeah. Great. That's the result, you mean? Yeah. Yeah, no, that's the surprising thing. I mean, in a sense, look, it doesn't solve the curse of dimensionality, but it sort of swaps the dimensionality for a different constraint, which is this norm constraint. So, I don't want to try and pretend it's complete magic, but it's a little bit of magic in that it does somehow give you a much more nuanced way of controlling the complexity of what you're doing. And if I do it, if I look at the next slide where I talk about the relative estimator, this is the empirical estimator, this is the true expectation. This is the thing that effectively is coming in that would be dependent on the dimension. If F was, if you like, independent in each dimension, it would become like a dimension bound. But, you can think of it in some way of, if you think of it in a Fourier transform, you might have F have sort of relatively small coefficients for the high dimension, for the more sort of high frequency components, and therefore you are able to get a good estimate. But a very general function that had, very, very complex behavior, obviously you would pay the price. So you're sort of, is that answering the question? It's, yeah. So it's kind of a way of looking at functions slightly differently.
There's no question. I would like to put a little bit of context on the talk. So this first part of the morning, we have kind of two schools represented by John and by Bernard in the next talk, which is the kernel methods and deep learning, which is called nowadays neural networks. And there was a time where neural networks were in the dark age, and SVMs came from, kernel methods came from theory were on board, and now it seems that kernel methods have lost the battle, and now deep learning is winning the battle because we are able to do all these awesome applications with vision, robotics, and all these kind of things. But so it seems nowadays that someone interested in machine learning or in data analytics has to make a choice, and the choice seems to be something difficult to make for someone that wants to go into the market. In the end, in the market, you have to choose a route to study, and both of them are really hard. So I would like, if you were able, any of you to make a comment, now that we have two school representatives here, what would you say to someone that is starting and wants to choose a route to make a career in machine learning? What would you tell them? What would you advise them?
I would say, as you've said, the flavor of the month is definitely deep learning, and probably that is where there's been most attention for the last short period. I think, it depends what kind of career you want, in a way. If you're thinking academia, there's, in my view, you need to know both. You need to understand how these different approaches have strengths and weaknesses, and that's probably also true in an industrial application. I mentioned at the beginning, I think where kernel methods come in their strength is where there's perhaps less data and you need a more clever way of regularizing, if you like, which is this that I've tried to illustrate with these examples. The magic of the deep learning appears to be that the structure of the networks actually is particularly well attuned to certain data types. And I would say it's not fully understood why. My intuition is that it's something about the invariances that are somehow implicitly encoded in the structure of the networks, so that when you're actually learning with those networks, you're somehow learning the classifier, but also the invariances in the data at the same time, which improve the generalization. But effectively, you're asking the thing to, the system to learn two things at once, and therefore you need correspondingly more data. Of course, from a theoretical point of view, it would be nice to understand how it's doing that, why it's doing that, and that I think is current research and is a very interesting topic of research. So in a sense, what I would say is from a practical point of view, if you've got lots of data and you believe the data will be appropriately handled by the deep learners, then that's probably a good choice. If you're probably not having as much data or your data is shifting in some way, maybe the kernel methods is an interesting avenue to explore. From a theoretical point of view, I think there's still plenty to do in both areas. Deep learning, there's lots of interesting questions to ask and interesting research to do, but equally in kernel methods, there's also a lot of, I think, current work going on and extensions and so on of kernel methods. Fair?
I'm not remembering what's the trend. You have a chance to defend in the next talk.
Yeah.
So, let's thank John for...
Okay.